So the eigenvalue stability is different from zero stability. It's a less severe. If a scheme is eigenvalue stable, it means two things. First of all, it's dependent on what equation you are solving. So you cannot say that the scheme is eigenvalue stable or eigenvalue unstable, right? It's conditioned on what equation you are solving. That's one thing. And two is that it's a less severe type of instability in the sense that you can rescue it by using a tiny time step. But it doesn't mean it's a good idea. You might have to spend a huge amount of computational resources to rescue the scheme from being unstable. So here, I think for the rest of this lecture and also a majority of the next lecture, we are going to be spending time on actually doing eigenvalue analysis. So I didn't get to the point of having you use your computer to do it in this lecture, but we'll do it in the next lecture, is to look at how can we analyze eigenvalue stability, and in particular figure out which for a particular equation, right, what scheme should you choose? Okay, and to get you started, let me actually give you a very simple hint on what is going on here. Okay, let me give you a very simple hint of what's going on here. So let's actually plug in this scheme, plug in this equation. I mean, in zero stability analysis, we plug in du dt equal to 0 into the scheme. So here, we actually want to plug in this real equation into the scheme and see what's going on here. So if we plug in this real equation into the problematic scheme, which is midpoint, what we get is u of k plus 1 minus u of k minus 1 divided by 2 delta t is equal to I minus 1, right? Remember our lambda equal to minus 1 times uk. Okay, so again, if we can write this scheme as a matrix form, can we write it as uk plus 1 and uk equal to a matrix? Now this matrix is delta t dependent times uk and uk minus 1. What matrix do we get over here? What's the second row of the matrix? 1, 0. Yes, thank you. Now the first row is a little bit different. It's no longer 0 and 1, right? The second, I think the second entry is still 1, but the first entry is no longer 0. What is it? Two delta t times I minus 1, right? So can somebody tell me what's the eigenvalue of this matrix? Well, of course, I can't just by looking at the matrix. So why don't we just invoke MATLAB and ask MATLAB to tell me what's the eigenvalue of this matrix. So let me actually call the entire thing. Let me just call this entire thing A. How about that? Okay. If we call this entire thing A, and in MATLAB, I can define a symbol A. Okay, I can just call A a symbol. I think MATLAB needs to invoke the symbolic math toolbox, and I can try to compute the eigenvalue of A, 1, 1, 0. I mean, have you tried this kind of thing before? No? Okay. What I get? I think the correct. Oh, I think the correct way is this. So here is what I get. Can I try to simplify that? Still get the same thing. So okay. So what you should notice is that I get the average of two things, right? So I get A divided by 2 and the square root of this thing divided by 2. And if I write it down, the eigenvalues are equal to half of a plus minus square root of, if you take this, it's basically, I have this 4 here, which divided by 2. I mean, it's inside the square root, so that's 1, right? So 1 plus half of a squared, right? So that's what the formula actually is. I'm trying to simplify to get to what I want it to be, but like it seems MATLAB thinks this is simpler than what I wrote. Basically, this is the lambdas, okay? And as you can see, if my A is equal to 0, which is for 0 stability analysis, my lambda is equal to plus minus 1, which we actually saw in the beginning of this lecture. But as long as A is not 0, we are going to start having problems. In particular, if A has a negative real part, okay? As long as A has a negative real part, we are actually going to have not just a negative. As long as A has a real component, we are going to have a problem being lambda having a magnitude going to be greater than 1. And that's what's causing the oscillations. Okay, the oscillations is going to be made smaller if you take delta t to be smaller and there A closer to 0. But nevertheless, we are going to have a slowly growing oscillation that ultimately makes the solution meaningless. So this is just analysis for the particular scheme for the particular equation. Next lecture, we are going to do a more general analysis and figure out what schemes is suitable for what equations. All right. Yes?
So does that mean that we have to like test every scheme versus the function that you're trying to approximate?
So good question. Does that mean I have to test every scheme against every equation? The answer is we have figured out better ways to do that than testing every scheme for every equation. So next lecture, we are going to be talking about what's called the eigenvalue stability region that we can actually draw out for every scheme. So for example, for forward Euler, we are going to be drawing out a region like that in the complex plane, and I can know that I mean that's for the imaginary part of A and the real part of A, and A, remember, is something like this. I know as long as my A is in this region, I'm going to be fine. And how do I take A into this region? By making sure the eigenvalue of the equation is aligned in this region and my delta t is small enough, right? I mean, these are the conditions I can ensure that the scheme is stable. So we look at the nature of the equation and we choose a scheme and make delta t small enough so that we are stable. All right. Any other questions? No, I will see you tomorrow, actually.